Now that's a contract. At this point, we've defined the names of the columns we want, but we still don't have a database. To actually make a database, we're going to extend Android's SQLiteOpenHelper. SQLiteOpenHelper contains cool stuff to create the database and help us handle database versioning. As we make changes to our database in the future, it will help us modify our tables. For many apps, being able to upgrade to a new version without data loss is critical. For Sunshine, we just want to make sure that upgrades that involve database schema changes happen smoothly. Let's take a look at SQLiteOpenHelper more closely in action. We're going to be working in the WeatherDB helper class that you've been given, which extends SQLiteOpenHelper. It contains code to create and initialize the weather database. Let's examine it. At the beginning of the DB helper, you can see that we've defined constants for database version and database name. The database version typically starts at version 1 and must be manually incremented each time we release an updated APK with a new database schema. The database name is the name of the actual database file in the file system, which will be weather.db in our case. Note that we're using version 2, since this revision of the course uses an updated database version. These values get passed into the constructor to initialize the database helper. Next, we have the onCreate method. This is where the SQL we've been talking about and our new contract class are used together. The first time the database is used, SQLiteOpenHelper's onCreate will be called. We need to write the correct SQL statement string so that we can create the table Sunshine needs. We then have the system execute this SQL by calling db.execSQL. Note how we're using all of the weather entry constants to write our SQL statements. Also note that we use lots of not null constraints on this table. These constraints help prevent us from inserting records without columns being filled out into the database, and that helps prevent bugs. Here is the implementation of the foreign key constraint from the not yet created location entry table. This means that we cannot insert a weather entry into the database until a location entry for the weather location has been inserted, and we cannot delete locations while there exist weather entries that point to them. That being said, it's going to be a while before we have UI that can demonstrate that our database code is working. Fortunately, there's a way we can have Android run any code we want, even if there's no UI yet ready. Android has a built-in testing framework that allows us to create a test APK that executes JUnit tests that call into classes in our main APK. If you aren't already familiar with JUnit, it is a testing framework that allows you to write automated test suites. You can run your automated tests easily. You can find your tests in this section of the Android Studio project. Just right-click on the test package and select Run. Once the tests pass or fail, you'll see the output down here at the bottom of the screen. I'm not going to display the emulator on our screen because it won't actually show that we're doing anything. The tests we're running don't have any user interface. But you can see here in the test runner, we're instantiating tests. An empty window and a green result means the test succeeded. Let's look at the test practice class. You can see it sits in the data package of our test project and extends Android test case. When you extend Android test case, you can implement the setup method, which will be run before each test. You can also implement teardown, which will be run after each test. Similar to JUnit tests, you simply add new methods in the class with the prefix test, such as test that demonstrates assertions, and those will automatically be run by the test processor. Some other things to note. The full test suite class contains code to include all of the Java test classes in its package into a suite of tests that JUnit will run. This allows us to easily add additional tests by just adding additional Java class files to our test directory. You'll likely have a class like this in each test project you make. They aren't typically project specific, so you can literally just copy this one. Each test should have at least one check, which uses an assert to see if the program supplies the correct output. An assert is just that. It's a declaration that the outcome after part of a test is run matches our expectation. If the assert does not match, the test will fail. Let's look at our test that demonstrates assertions in testpractice.java. Assert equals asserts that the expected value equals the actual value. If they are not equal, then an assertion failed error is thrown with a given string message. Other useful methods include assert equals, assert false, assert null, or we can just call fail if a certain code path should never have been reached. Feel free to write your own test cases to play with assertions. Let's see what happens when we make a test fail. As you can see, our results are now red, and we can see exactly where in the test our application failed. Let's uncomment out the test_create_db function inside of the testDB class. You might have to import a few classes to get this to compile. Let's also uncomment out the create North Pole location values and the insert North Pole location values functions from within test utilities. This is the last chance to fix up your location contract if things don't compile. So let's run our new test with our testDB. As you can see, we get a pretty good error message back that our database was created without both the location entry and weather entry tables. Don't worry, we can fix it.